Right. Okay. So anyway, it's a great pleasure to welcome you all and to welcome in particular Augusto Marcelli from the Italian attaché, as an Italian attaché in Stockholm, right?
Yes, but I'm not here as a scientific attaché.
No, I know you're not, but that is one of your roles. I think we met about 18 months ago, maybe 2 years. I'm not even sure. I can't remember. And it's been nice interacting with you, and it's in particular pleasure to welcome you to the new LINXS, and this is the second event. We had one last week, but this is the second event that we've had. So it's a great pleasure to welcome you here and to listen to your talk on time-resolved spectroscopy. So welcome, and welcome to you all.
Okay, so tack så mycket. I'm very pleased to be here. I'm very pleased also to be the second, because I don't like to be the first. Because it's important to be within the first. That's and I think it's very important to be in the first position, but I don't like to be really the first. It's too risky, and sometimes okay, so I have to cancel this. Okay, then I want to acknowledge LINXS to host me, and I want to acknowledge also Sweden that is hosting me in the official position. And I think that what I'm going to present could be interesting even to discuss and talk about science, because I love science. It's my real life for more than 40 years. And I think this is something that could be considered a legacy of a scientific story, because born from an idea, and it took a lot of time, so almost 2 decades, to understand what is contained in one picture that I will show you later. And I think many of you, according to your interest, we can understand what I'm talking. Okay, so I need to use this. Is this working?
One question is the fog press?
Okay, don't worry, I can press. So first of all, I think it's important to acknowledge, because any presentation as a piece of the story, it's the results of many collaboration. This is science. Sciences cannot be done in on a desktop in a room. Science can be only done interacting with people, living, and even places like this, like LINXS, are fundamental, because people met and discussed. Maybe you are discussing of something which is not correlated with your job, but then after you discover that it is exactly what you are thinking and what is useful for you. Because what you need to build is mind. If you build the mind, we can get anything. And so this is just a partial list of all the persons that contributed to my knowledge and the results I get. And as you will see in the logo, there are also industry. Because science is strongly correlated with industrial activity. Industrial activity is the end of the story, but without the head, without the thinking, without the mind, there are no industry, okay? Science is at the base of the society at all levels. But the industry are important to make progress. If I have time, I will just illustrate the one piece of the story at the end. Okay, and then I have to acknowledge my lab, because without the lab, without the person, without the technicians, without even the director that listen you when you ask for money or for space or for something, you cannot do that. Okay, and this story is quite old, because it is very interesting to see. This is the first page of the first issue of a physical review. At that time, the name was Physical Review, not A, B, C, D, etc., etc. And the first paper published in Physical Review, just in 1893, is a study of transmission spectra of certain substances in the infrared. So it's even the title is very interesting, because this is a study on certain substances that goes from polymer to plastic and so on. and using the infrared. So infrared has been, for physics, one of the most important probe to understand the matter. But in the early age, we just distinguish materials and properties. The evolution of the next, as we will see, is dynamic. We are not interested to distinguish wood from plastic or from metal, but we want to know how they behave under certain conditions. So that is much more difficult. And that's just in 130 years. So in more than 1 century, we move really the knowledge in a completely different way. And so the story of this seminar is essentially linked to this very simple slide. That is my Cinderella shoes. So I found these shoes and I look after to the Cinderella. So let's say to the background. And why it's very important, this slide? Because this slide connects time with the phenomena. And what does it mean? It means that we know many of these phenomena, from electronic excitation to vibration up to rotation. And then behind, there are phenomena which are connected to life science, to biological behavior. That's because this lecture was given by one of major Italian theoretician, Tosi, talking about the design of new drugs. So about 30 years ago. So how to design new drugs. That was before machine learning, artificial intelligence, and so on. And you want to know how to design molecules that can modify conformational changes or electronic transfer reaction, enzymatic reaction to try to fix pathologies. So that was the early discussion on this theory. So what does contain really this figure? That's not very simple. So the question is, what does it mean? And how it may be useful if I understand the content of that. So one of the first consideration is that different time or different frequency correspond to different phenomena. So you can essentially distinguish different phenomena because they happen at different time, different frequency. And the second consideration is that if you want to probe this phenomena, you have to change the energy. So in which you probe, because you cannot see with X-ray something that goes to very long wavelength. Okay, so it's transparent. So this is very important because sometimes you want to study a phenomena which is working in some frequency range, but you use a different probe and you don't see that. And then the second consideration is that any time resolved approach based on vibrational spectroscopy, so I mean infrared, terahertz, or even Raman, can explore dynamics for sure, but there are limitations. Why I mention vibrational spectroscopy? Because my scientific career born with X-ray, okay? So I was a spectroscopist. Actually, spectroscopy of rare earth, before the discovery of ITC superconductors. So when we discovered that oxide were superconductors, I were already in the field because there was a lot of information and so on and so forth. But the X-ray are damaging. X-ray modify the systems. And then the interest was, okay, try to use a different kind of probe, which are vibrational spectroscopy. But then you have a limitation which are associated to the time. Okay, so to get deeper into this field, I will try to make a brief story of infrared microscopy. And microscopy is very important because microscopy is connected to imaging. That was also the big step further in the science of the last decades. We move from a single point analysis to imaging, to a description of the system on a larger scale. Because, for example, just to be clear, if you want to study a dehydratation process and you study just one single point, maybe in that point there is water, or maybe not. So only if you map the system, you can see if water exists, if water has a dynamic, and where. So the single point analysis is extremely key. And the second, and there are also very important information connected to the analysis, which are related to the optics. So we need to understand much better what source we are using, what is the brilliance, what is the diffraction limit, and so on and so forth. And the interest is because, of course, nanotechnology emerged in the time, but to go from microscopy to nanoscopy, it's not easy. And even now, it's still very complicated to make nano imaging at real level. Okay, so it's funny to see that this was the first commercial infrared microscopy. And that was done by an industry, Perkin-Elmer, in 1954. Okay? So 70 years, it's almost the same time from the Apollo on the moon. When we started to make the discovery of the moon in the 70s, it was 17 years ago. Okay? So it takes time to make progress. Until 1990, nothing almost happened because this was really a very simple instrument. Even it was quite sophisticated because the big advancement was the manufacture of cast grain objective. And cast grain objectives are very important because they allow to illuminate the sample with a significant amount of light compared to the past, with normal optics. And the third one, which was very important, is that we could, with electronics, with computer, with PC, increase a lot of technical, let's say, acquisition. So we increase the imaging speed and the sensitivity because we could manage with the computer the simple linear array detectors. Remind that in the early stage, we have only one single detector. And then with the possibility to have an array of detectors, not matrix yet, we can change along the line of the detector and use this as a time. So instead to measure in the same point of time, we can have accumulation on a linear detector, different time, and try to monitor the evolution of the system. The other huge advancement is associated to the sources, because in the infrared, we had the possibility to use synchrotron radiation. Why synchrotron radiation has been extremely important for vibrational spectroscopy? Because this is the comparison of a black body, so it's a normal conventional source for any kind of infrared experiment, which is essentially determined by the temperature of the black body. So if you have a black body at 1200 Kelvin, that's typically the emission and the spectrum that you can cover. And you can see easily that any kind of synchrotron radiation facilities, no matter of their energy, has a huge amount of flux, more than a black body. So the brilliance of the synchrotron radiation, which means the dimension of the source compared to the divergence and the size, is much higher than a black body. What is also interesting is that synchrotron radiation is not a thermal source. What does it mean that it is not a thermal source? That the thermal noise does not exist. So you are limited by the intensity here and by the thermal noise. This source has no thermal noise. And so this is an effective advantages that allow to squeeze the pinhole to reduce the illumination size and to get still a high signal to noise ratio and a high intensity. This made possible to do really microspectroscopy up to dimension at that time of 20, 30 micron, which were not accessible to black body. So the advantage of synchronous radiation was essentially for higher brilliance, which means the ratio between the flux over the divergence and over the dimension of the source, no thermal noise, extreme collimation, and high spatial resolution near the diffraction limit. Okay. Now focus on concept, space. So now we have to do experiments, and then we have to focus on fundamental concepts. So what can explore in terms of space with the source, and then we will discuss time, and at the end, space plus time. Okay, so this is a very simple concept. I don't know exactly the audience, but sometime for many of you, it will be very simple, this concept, but it's important just to remind when we want to do imaging, we want to distinguish two different elements, two different components within a sample. So we need to be able to resolve in some way the two components in the sample. And that's it depends also by the wavelength that we are using. Okay? And essentially, when we try to focus with an objective, the light, at the end, we essentially see a spot of light, and the spot is not really clear, it's essentially associated to a waste, so with a diffuse light, which sometimes, if you have good instruments, associated to a diffraction pattern. Typically, we see the first diffraction, but we can observe also the ring associated to the main spot. And this is clearly an example. So the resolution allowed to distinguish in instruments just a general waste, or maybe a pattern in which it's clearly visible two different regions, or maybe in the best case with extremely accurate optics and a high brilliance source, two extremely different spots. That is a typical problem in astrophysics. When you have a large map, large imaging, and then you need, and you have now machine learning procedure that from the basically clouds recognize at the end two spots. Okay? And application of machine learning, it's extremely important to go from here to here, even with the limited optics in anything. There are many kind of resolution criteria, but the most important information is that the dimension of the beam in the focal position of an optical system is typically given by this very simple equation. And this simple equation is except the coefficient, it depends by the wavelength. And this gives you clearly information that if you use X-ray or infrared, we have clearly a different resolution because X-ray are much more smaller than vibrational light in the vibration. The other important thing is that there is N, which clearly depends by the materials that you are studying, and then there is this sign of theta, which is the parameters of your optics. Larger is the theta, the angle of your optics, larger the possibility to collect light emitted by the sample, and higher would be the resolution of the images. So there are not very much parameters to manipulate, and then also the reason because optics until now is basically the same optics of the past. So what is going to change now is the diffraction optics. like zone plates or other things. But the optics is basically similar. And also it's very important to understand the diffraction limit. It's a principle. No one has physically explained the origin of the diffraction limits. I mean, the diffraction limits can be seen in some way as a quantum phenomena in which the localization of the light is associated to the Heisenberg principle. So if you strongly localize the light, then you lose the information of the energy of the light. That's is one way in which you can probably interpret the diffraction limit, and it is still a matter of discussion. What is very important is also another parameter. Then in general, when you focus the radiation, you lose a part of the intensity, because in the main spot you can get no more than this. The other part of the intensity goes in the diffusion, in the higher order. Then if you have two optics, one in sequence to the other, then the second optics will lose another 16%. So any additional optics make you aware to lose more intensity. So the basic message is that the resolution is essentially depending by the numerical aperture of the optics and the light, the wavelength of the light. Okay? Then you can manipulate a little bit with the N and so on, but it doesn't change much. Okay. So now this is the crucial point, and also the major aspect of infrared microscopy and vibrational microscopy. So since you know that you lose a part of radiation with the optics, so you want to minimize the number of optics, and also you want to optimize the resolution. And this is a theorem by LINXS in the 60s. If you want to get a microscope with a better configuration, the only way is to have a confocal configuration in which you have one aperture on top, one aperture on the lower, the two optics on the lower part. Then you have only two identical optics, and that's give you the best resolution in the system. So no matter of the source, no matter of the detectors, that is the only optical configuration that you can use to get the best resolution. And if you have the best resolution with high source, you can explore space and time analysis in the best condition. That is also the problem of X-ray, because in principle, if you want to extend this to X-ray, to have a confocal geometry for X-ray, it's extremely complicated. It's possible, but it's not easy. And the Minsky theorem say that the product of two identical A function, because the distribution of the spot, the main diffraction spot and the waste, is called the A function, and the A function is 30% narrower if you have this kind of configuration, and that is the top. Okay, this is the point that's also very important to understand. Localization and resolution, okay? If I use only one objective to focus the light on a sample, I can focus very well in one direction, but not in the other. But I can improve the localization of the light. If I use two objectives, then I will squeeze also in the other dimension. But this does not mean resolution. This means localization, which is a different concept. Okay? So I can increase the intensity, and that will help me to get higher signal to noise ratio and distinguish different figures, but not change the resolution. The resolution displayed by the other equation. Okay? And this is the important question that opened this figure. A focused spot may be considered the unit capable of extracting information from the system in analogy to a photon, the minimal unit of radiation in quantum mechanics. So this is an area which is, from the theoretical point of view, still unexplored. There are hundreds of pages of book in which we want to understand these aspects. Okay, so now this is also very wonderful examples of the use of singular radiation. It's an old experiment of 90s by Carr, in which it is experimentally demonstrated what I said. Okay, so if you have a single aperture, changing the wavelength, you can measure the spot dimension. So your capability to resolve. And then you see that with a single aperture, so remind the Minsky theorem, you can have two systems, confocal, and then you get the best. If you have a single aperture, you can go in this way, and then you decrease. If you have a confocal aperture, you can get much better resolution, but then at the end, you are limited by a source. Okay, so that's an experimental demonstration. And this is also zero. Okay, resolution pattern full with half average, half maximum. At the end, the size of the aperture is equivalent to the wavelength of interest, and this is the best choice that you can get. Okay, let's now go to see what does it mean. All this. This is our experimental data in which you can have two cells, which are these are the images of the two cells, the same two cells, the same condition, in which you play the game of the optical parameters. Okay, the optical parameters that we manage are of course, the different aperture, the detectors, the size of the detectors, and a little bit of statistics. You can see that there are differences. Here you don't see almost nothing. You clearly see the resolution, and you still see something, but not with the same intensity and resolution. And how it may happen. So that's the reason, because when you read a paper and you see a figure, you have to go to the details of figure capture and you see how it's being collected. Because it doesn't mean that this is the best way that you can do it. Okay, so this is the number, just to go, I don't want to go in and bore you, but it's very interesting to see that this is a resolution of 6 by 6 micron, clearly. This is a resolution of 2.5, and this is similar spatial resolution, but what is completely different is the signal to noise ratio. Okay, so this is more than 1,000 signal to noise ratio resolution. This is 500, and this is 20. Still, even with a lower signal noise resolution, you get this. Because this is a combination of source, optical parameters, and detectors. Okay? So you need to optimize the parameters, not only one. And what is the other parameter that you're looking for is the magnification. This is times 4, and this is times 15. What does it mean? The numerical average is the collection angle. If you collect all the radiation diffused by the samples, you can get more information, even with a lower signal to noise ratio. You can get higher signal to noise, but your aperture is lower, and then you get less photons, and then you get less information. That's correct? So that's the way, how much is complicated to manipulate this. It's another very illuminating, let me use this adjective, explore the difference between a conventional source, is a global, and a synchrotron radiation. Why it's very important this? Because when I have a lot of photons, I can tune, okay? So I can adapt my source to the sample I want to study. And this is a clear example. So if I use a global, the global illuminates everything in a homogeneous way. If I use a non-thermal, extremely brilliant synchronization source, I'm not able to illuminate all the vectors. But this is not a disadvantage. It can be an advantage because I can tune and I started to widen until I illuminate all the samples that I want to illuminate. So what does it mean? If the sample is smaller than this, I waste a lot of energy, intensity, and photon. And then in this case, I can focus much better and I get the best. I'm sure that you are surprised of this, but I will show you that it's true. That's, for example, is the images we got in Frascati with 1.5 ampere, which is typically 5 times the intensity than any other synchronization source. And that will allow to see and distinguish very well within the cell the distribution of some components. That is just to give you a feeling. And that is an area of 80 by 100 micron. And then we put the synchronous radiation only in this domain, spatial domain. What does it mean in the reality and from the physical point of view? Okay, so this is the images of the cell. These are the vibrational spectra. And these are the comparison of global images and synchronization images of the same cell with the same radiation light, with the same optics, etc., etc. And the question is, those images are similar or identical or different, and why are different? So let's look at the first two. This is concentrated on the amide 1 band. And you see that these images are quite similar, but the background is completely different. If I go to the CH group, again, are quite similar, but there is a contrast, which is very different. So now we learn another important word, which is contrast. When you do imaging, you want high contrast also. And in the zero groups, again, you see that there are similar images. It's not always like this, but the contrast is completely different. And let's say, why we want to use synchronous radiation? These images seems better. It's correct? So these images seems much better than this. Okay. Then we can change and do similar analysis, but we go on a different samples with different size, and now the scenario changed completely. Again, this is global. This is synchronous radiation. Here, there is signal. No. Let's say we say name. So if you are doing this examination with a global, you miss completely all the information. While you go synchronous radiation, you go. So that's to clarify clearly from the experimental point of view that the control of the parameters is very important. What is the difference? This image was much larger, and then the global illuminate much better. This was smaller, and then the global is wasting a lot of energy to improve these images. So the contrast was lacking. And this clarifies the point. Global illumination, similar. This is synchronous radiation illumination. I want to illuminate this or this. Clearly, there's much more intensity and higher contrast, and I see something that with the global I cannot see. I have another parameter. I can squeeze the brilliance, okay? I can increase the capability of my source, okay? Single cell, so I need the highest brilliance as possible. I cannot do nothing with global, this is the illumination. But I can tune the brilliance of the light source, and I can try to focus on 3 different wavelength regions. And then I can play the game of brilliance, okay? So you have another knob to turn, okay? Let's see. The parameter is the current of the facility, 0.6 milliamp, that's amp, so 600 milliamps, okay? These are the images in 3 different regions. We call 1, 2, 3, that doesn't matter, it's not relevant. And then you see that with the singular radiation, we illuminate this region. That is very important because the majority of beamline in the world work in this region, more or less 600. Take care of the contrast, okay, of the images. This is no signal, nothing. We are most double. Look to the comparison with the global, okay? These are the images that you can take at home with your infrared source. And then with this simple line. Do you like it? Okay. So in this wavelength regime, probably the global is even better. But if you move here, does it make any sense? Or if you look here, that's the reason because you need to understand very well your experimental tool. Okay? If you are until here, you can be satisfied, but there is no real advantage. But if you go in this regime, it is clear advantage. This could be interpreted as a machine learning as a donuts, if you work. But you have to know that this is donuts. Okay? And you start to discover this at the end, I mean, at the initial phase here. How many LINXS still I have? More or less.
Maybe 3 or something.
Okay, so now I try to give you the relevance of the space, how to control the space in the images to distinguish the materials you are studying. Now I want to focus on time because systems evolve. And what you say in an instant, after some instant, an instant can be microsecond, millisecond, femtosecond can be very different. Now we are exploring attosecond, so you can imagine. Attosecond is really the domain of quantum, where localization is a really important concept. So, what we can do if you control the time in addition to the space? We can have a lot of possibility to explore dynamics. And in particular, if you look to different kind of experiment, the best one for sure is simultaneous experiment, but then you can have time resolved imaging and so on and so forth. One important aspect that you can study equilibrium versus non-equilibrium phenomena, which is very important and which are completely different, or metastable phenomena. Okay, this is my story now, what we did in practice. So we started from this, and we try to put some numbers, some figures on this. Okay, so this is our 3 bars that essentially confine three different domains. Microsecond domain, nanosecond domain, and then up to the femtosecond. That is very important because microseconds versus seconds are phenomena that involve big systems. Okay, proteins dynamics is in the microseconds, for small proteins up to seconds or even longer. Nanoseconds are phenomena which are involving molecules, very simple. Bonding of ions and so on. And a femtosecond is electronics, dynamics, and so on. And that's one of the first games we made is the cover of Journal of Physical Chemistry game some times ago. And then we studied the evaporation of the drop as a proof of concept, showing that time-dependent phenomena can be successfully studied in the infrared energy domain. Why this dynamics is important? Because our life is based on the drop of water. Weather is the change of drop in the clouds, in the atmosphere, on the ground, as a form of ice, snow, and so on and so forth. So if you know the physics of drops, we know the physics also of many industrial processes. If you put a paint on a wall, if the liquids evaporate too fast or too slow, you get the different patterns on the wall. So this is just a very simple example. And so we made the first experiments in which, using two different tools, so two different instruments, we measured one phenomenon. This was an experiment that we made in Bessie. And then we use Bruegel instruments IFS 66 to measure the terahertz using the synchronous radiation. So terahertz radiation from the beam, from the synchronization beam, was going to the EFS and then going to the bolometer. Then simultaneously, we use a global source to collect on the same sample the big infrared radiation, and we collect with this detector. So this is the experiment. The main problem was how to start the experiment with two different instruments which are not connected together, because that is also very difficult. Then these are interferometer. So the interferometer calculate automatically depending by the range. So the different space of the acquisition has to be readjusted and so on. It's very complicated. This is a view of the internal part of the instrument when you can understand that the light is coming on the sample and the other is at 90 degrees. If you couple all together, I have also tell you that typically water has a long evaporation process. A normal drop, assuming that exists a normal drop, can take several minutes to evaporate, because it depends also on the humidity in the atmosphere. If you use ethanol, methanol, you can go faster, but typically this is the time of the evaporation of the drop, which is tens of minutes. And so you see that it's very interesting, this dynamics. 43, 44, 45, 46, and then it's faster. Because the evaporation of the drop is a complex system that depends by electrostatic, gravity, chemical interaction, interaction with the substrate, presence of impurity, and so on and so forth. So just the evaporation of a drop of water. So what we are interested to see this is clearly noise. Of course, we made an evaporation of deuterated water, because otherwise, at the end of the process, water present in the atmosphere getting to the drop can change the dynamics. So you want to distinguish exactly water in your experiment, and then we use D2O. Then we monitor some of this process. Okay, so this is just to give a feeling, the number of spectra you collected during the evaporation, and you clearly see that how this evaporates. And in a 2D, you have this very nice pattern. And you are interested, of course, to many things. This is one component of the spectra of the evaporation of drop of water versus time. And this is more or less the trend. Okay, then we focus on another one, which is not exactly the same pattern. So this component of the vibrational spectrum doesn't replicate the first one. And this is also clear from these 2D images. And this is in the Rydbergs domain. You can see there is much more noise, and the pattern is completely different. So the chemistry associated to the evaporation cannot be monitored looking one component, but you have to look to everyone. And this is the first experiment in which you monitor in the Rydbergs. Why in the Rydbergs? Because in the Rydbergs you can monitor all from the early stage. Look, this is the change in the mean infrared. You see, it's clearly pattern which is decreasing. In the Rydbergs, it's completely different. Sorry. It's not the same shape. Okay. You can use this to monitor very complex phenomena, like, for example, the ring stain, in which you see after some times that there is a mechanical dynamics that bring the components into the external grid. Also, this is an important industrial process for glues, for painting, and for nail. And this is spectroscopic images in which you see the components of materials that move to form a ring. You can do this also in electronics sometimes. And we studied the first stain mechanism versus time. This is an experiment in which you see how the chemical components move from one part towards the external. This is a sequence of, but you clearly see that the image is changing from a zero intensity up to the top of intensity. This is an experiment in which you monitor the water and the methylene blue. The stain phenomena is what happened in a coffee cup when you drink all the coffee. At the end, the powders remain in the bottom, and you see that they form some pattern. Okay, we simulated the most typical stain effect with the methylene blue, and we start the process, and then we monitor in one point of the space where the water or the methylene goes. Here you see the time, 180 seconds, more than 220 seconds, and so on. 300 seconds, 366, 400 seconds, okay? We are monitoring here, of course, the intensity of water, and then you see that this is the edge of the drop, and the edge of the drop move, and then disappear. Then, if you monitor the methylene blue, is exactly the opposite. At the edge, 180 seconds, there is no methylene blue. And at the end of the process, the methylene blue has formed a perfect ring with the top of intensity. Okay? And you can clearly see how the methylene blue peak at the edge of the drop at the end of the process. Here there is another example of time-resolved structural dynamics, which is much more interesting. Much more interesting because it contains also the information on time. Okay, what is this? This is an infrared spectroscopy experiment in which you have a film in a liquid phase, like a salt gel, which is going to dry. And if you see from the top, these are all the spectra in a certain time range. You see from 23 to 47 seconds. These are the two main components. This is a film that contains silicates. This is a silicon oxide silicon, CH and OH. And if you see the plot from the top, there are two regions which are extremely different. One which is flat background, and another one which are clearly are present waves. What does it mean? When you have a film, liquid, the surface is very flat. And then it is like a Fabry-Perot film. So the film evaporates, then the size of the Fabry-Perot decrease. This means that there is an interference, but the interference will move in time. And in fact, the interference is determined by the wave which move. Okay? At a certain point, the wave disappears. It is clear. You see, these are the waves. And then after 35 seconds, the wave disappears. Why the wave disappears? Because the film is not more liquid. You generate a solid surface. A solid surface is not more flat. And then you destroy the interference. And if you destroy the interference, then you get a solid phase. So this is a way in which you can monitor a liquid to solid transition. And what is very nice is that the change of the dielectric constant is visible here. You see that the peaks change because in this moment you change the dielectric constant because the dielectric constant of liquid is different from solid. And if you see in this domain, everything happens into the microsecond domain. We cannot see. You see, we lack information. So if you want to explore the really solid, liquid to solid transition, you need a much higher time resolution. But it is here. You can. So this tells you that you need space plus time. Okay? That's, I was thinking to this, then reminded the slide. Now I realize that I can do something. And then when you think that you can do something, there is always someone that already did. You have just to look for. That was a paper published on Science. I didn't know this. When I publish my paper, you will see, I didn't cite. Then I discovered, and then I phoned to Brass and I say, sorry, I forget, because I didn't know that you already published a similar idea. I didn't do the same experiment, and also I want to notice that this time scale is means. This is an experiment, time resolved study of structure development and reaction kinetics of polymers, and that's in a scale of means. This is a paper published on Science, and I show that the study confirmed that the driving force for the structure development in a polyurethanes is the thermodynamics of phase separation. And that's because the knee happened several minutes before the change of infrared. That's with the signal to noise ratio of that time. Probably if you do again this experiment, maybe not, but this is clear that the knees start before the change of vibration components. Okay? What I did with my colleague is something similar, but much more faster. And I think this is the main consequence. We clearly know that there is a convergence of simultaneous and time-resolved techniques, and that is fundamental for analytical analysis in the future. Also, for another aspect that I want to focus, that's this fantastic paper by Felix and Quake on the biological frontiers physics of 2006, so 20 years ago. what this picture tells us. If you try to calculate the electrostatic energy of a spherical shell, the bending of a rod, the fracture of a rod, and the binding energy of an electron in a box, then you see that these trend change with the length and the energy. Okay? If you decrease the energy, this decrease and peak to this length. The other components of systems like electrostatic energy or mechanical contribution has a slope in the other direction, but almost all converge to a length which is the length of chemical bonds, more or less. Then you have this white line, which is the thermal energy. So if you change the energy, the thermal energy of your system, you can goes up, and then the system can peak energy or not. But so the behavior of a system, when you go to this scale, is extremely dependent by the different amount of this and from the thermal band. Okay? And then if you want to know how it works, you need to control all these parameters. If you want to see how the chemical bonds, you need the X-ray. If you want to see vibration, you need the infrared, and so on and so forth. So what you're looking for, what is your question, what is your goal? Since I have a few minutes, let me skip to the soil gel chemistry. The soil gel chemistry is a fantastic process in which, according to the humidity, the presence of an atmosphere, you can, from an isotropic solution, goes to the formation of a liquid crystal, so a structured system. That's it's fantastic application. And then we perform a time-resolved simultaneous spectroscopy. That is the cover of the paper when we published, and trying to combine SAX and infrared spectroscopy. Let's go to the data. So this is a silicon buffer where you can have a thin film, which are going to self-assembly. Then we have the SAX detectors. So we send X-ray beam and infrared beam at the same time. With the SAX detector, we collect the pattern of the small angle scattering, and with the infrared, we collect the vibration spectroscopy. Okay, that was the very complicated setup. In a few centimeters, we realized 2 electra. It was very funny because after the publication of the paper, a couple of persons called Brugger and say, we want to buy these instruments, but these instruments was just something like customized, not real. And you see the light in the X-ray, which is going to the sample. Then there is a simultaneous infrared that crossing the sample. And then you can have this typical spectrum, okay? SAX and infrared. Well, let's see the experiment in a real time. 0 seconds, 2 seconds, 4 seconds, 6 seconds, 8 seconds, 10 seconds, 12. Much more. So you see clearly that there are 2 different behaviors. The SAX tell us when the structure forms. Okay? There is no structure. When the structure starts to appear, okay, between 8 to 10 seconds. And here the spectra almost disappeared, so the infrared, the vibrational components. What does it mean, this? Okay, this is the kinetics. We see after 8 to 10 seconds that you form the structure, so the film becomes ordered, and that's depended by the ethanol and the water. So this is the ethanol. So when the ethanol after 8 seconds is almost disappear, then you start to grow the structure. And then the water is slowly going away. So you can distinguish the different components inside the materials that trigger the process of order. Okay? And then we move from the minutes of the experiment of brass to the seconds of this experiment. Now this experiment can be done even in the millisecond domain. So you can explore much more accurately all the components. And so this is the relevance to have this kind of experiments. For example, you can study system like this. This is an analysis we made with a Japanese colleague, in which you can use the infrared to monitor the formation of this pattern, which are like gratings, in which you combine the process of coating with the UV curing. I mean, for example, you put your liquid film, then you illuminate with the UV radiation with the pattern. In some region, UV deform the materials, and then during the evaporation, the materials behave in a different way. Okay, so you can use the combination of technical methods to obtain just with optics a real system. This is a great puzzle. Okay, I think I can finish now with the perspective. So we just give you the feeling that we need to improve techniques and instruments, but we need to control very well the instruments that we have to get the best. But then we need to work also on the sources. And the future of the sources, in particular in this field, is quantum cascade lasers, because the quantum cascade lasers are powerful like a synchronous radiation, but are coherent. So we can explore the coherence of the light and probably goes beyond what we do with synchronous radiation. And then we can also explore the nanoscopy with the near field experiment, and that will be fantastic with free electron laser. And this is also what I think is very important: combine different energy. So different probe at the same time can give you really the feeling of what's going on. The experiment I showed you before can be done independently. So I can do SAX and then I can do infrared. But then I need to know where is the zero. If I don't know where is the zero in time, the two spectra can be completely displaced. You can understand what's going on because you know when the zero starts. Okay? And this can be done only if you do simultaneous experiment. Thanks very much.